There are several factors that affect the reaction rate. For example, the first one we'll discuss is temperature. Generally, as temperature increases, the rate increases too. And the rate constant, K, that also the value of the rate constant also increases as temperature increases. And this is a very important information, that rate constant approximately doubles with every 10 degree Celsius rise. Now, collisions. Now, in the collision model, we assume that reaction occurs as a result of collision between the molecules with the correct kinetic energy and orientation. Now, so the minimum energy that is required for a reaction to occur when molecules collide is called the activation energy, and we write it down like this, EA. Now, when the molecules are colliding, the orientation makes a big difference, because some of the collisions are not effective if they are not colliding properly. So the number of collisions that are favorably oriented, which are resulting in the formation of a product, is described by the frequency factor A. So here is the Arrhenius equation, a very important equation that relates both of these factors to the rate constant, temperature as well as Arrhenius factor, frequency factor, also known as Arrhenius factor. So you can find out the rate constant if the temperature is given to you, Arrhenius factor is given to you, or an activation energy given to you. The best way that we can utilize this formula is using the graph, because this was the equation K equals E negative EA over RT. And if the equation is written in the exponential form, you can always write it down in the ln form. You take ln on both sides, and then you apply the ln formula, ln A plus ln e to the power negative EA over RT. This comes on the front, and ln and e get cancelled. So what is left? Ln K equals, and I'm writing this part first, this cancels, negative EA over RT. This A is just a subscript plus ln A. And again compare it with the linear equation, that if you draw the graph, so here you can write, if you draw the graph between 1 over T on x-axis versus ln K on the y-axis, you will get a straight line with the negative slope, and the slope of this will be EA, negative EA over R. This is one way to find the activation energy graphically. If you are given, let me see if it's on the here. So if you have the K values given for two different temperatures, then you can write down this equation, ln K1 over K2 equals EA over R 1 over T2 minus T1. This is the equation that you can use, that if the two rate constants at two different temperatures are given, then you can find out EA value, because we can just plug the value of R. What is R? It's a gas constant, and you use the value 8.314 joule per mole Kelvin. And temperature, keep in mind that in all of these, temperature always have to be in Kelvin. So here, look at this problem here. The rate constant for a chemical reaction increased from 0.100 per second to 3.30 per second upon raising the temperature from 25 to 45 degrees Celsius. So here, what is the activation energy of the reaction? So K1, 0.100 per second, K2, 3.30 per second, T1, 25 degrees Celsius, which in Kelvin it is going to be 298 Kelvin. T2 is 45.0 degrees Celsius. In Kelvin it is going to be 318 Kelvin. So you can use the formula ln K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. Plug the values. 3.30 equals EA over 8.314, 1 over 318 minus 1 over 298. Let me show you a little bit more work. Negative 3.497 equals EA over 8.314, and when you're going to 1 over the parentheses, you should get negative 2.11 times 10 to the negative 4. You can cancel out this negative sign with this negative. This comes in the denominator, this goes in the numerator. Your EA should come out 138. It will come out 138 138,000 joules per mole. Why? Because R, you are taking it 8.314 joule per Kelvin mole. So, but if I have this number, it is good to write it down in kilojoule. So at the end, just write down 138 kilojoule per mole. Catalyst also plays a role in increasing the rate of a reaction by decreasing the activation energy of the reaction. And how does it work? It basically changes the mechanism by which the process occurs. Now again, catalyst can help you to increase the reaction, but it cannot make the reaction happen. So for example, if you have, let's say, a reaction taking place like this is my reactant, this is my product, and this much is the activation energy required for the reactant to produce the product, then in the presence of catalyst, it might go like this. So what it did, it lowered down the activation energy so that the reaction can, so the rate can be increased.